Okay, so welcome to another lesson of OpenStax Astronomy. We're going to be covering Chapter 2, Observing the Sky and the Birth of Astronomy. So we'll be looking at a bit of how the sky appears to us, and then a bit of history of astronomy as well. So the sky above, we talked about how stars are different distances, but from our vantage point, they all kind of seem to appear just in the night sky, what we'll later talk about of a celestial sphere. They're just kind of all hovering over us. So our apparent view and the actual, layout of the stars in the night sky is slightly different. So let's start off with constellations. And there's 88 of them. And constellations typically now today are really used to just map out regions of the sky. So if you ever looked at a map of the United States and you see the different states broken down to identify territory, same thing for the constellations. They make up different portions. Collectively, there are 88 different regions there. And an asterism is an easily recognizable group of stars. So an example of one is the Big Dipper. So the Big Dipper is not a constellation, but actually a asterism. The Big Dipper is part of the Big Bear Ursa Major. Here we have an image of Orion, constellation of Orion here. And so to us, we just kind of see some stars that are, gathered in a pattern. But it takes a bit of imagination to kind of try to relate, what images were there. But Orion here is the three stars are the belt. And then Betelgeuse, which is on the top left here, that is the armpit of Orion. So again, requiring perhaps a bit of imagination for that. And that's the great warrior in the sky. So the celestial sphere is the apparent, the appearance of the stars. If there was kind of this dome, if they were all of equal distance of how they would actually look around us. So they're at different distances, but just how they appear to us. So the 88 official constellations cover the entire celestial sphere. A bit of vocabulary when we're looking at the night sky. The zenith is always the point directly over your head, and the horizon is directly in front of you, so 90 degrees away from the zenith. So hence the horizon. And the Earth has a slight tilt to it, so 23.5 degrees. So our north doesn't actually align with the sky's north, so what we call the celestial tilt. So we're slightly off center, and so that kind of changes our celestial equator, the ecliptic. And so a couple of definitions here. We have the North Celestial Pole, the South Celestial Pole, and then the Celestial Equator. And then, of course, the ecliptic, which is the path that the suns and the planets tend to go around. And from the image here, we could see that they are slightly off-center there. So here we're looking at the celestial sphere, which is kind of this imaginary dome around us here. Right from the top, it appears as a dome, but again, two portions there. And all the stars to kind of appear as they're on this sphere here. And so there is an equator on that sphere. And then we have the South Celestial Pole down below. And the Earth, since it has that slight twist to it, then we see that this equator here is going to be slightly off there. And actually, it's right here, the ecliptic, right? So right on here, we're going to see that is actually offset by 23.5 degrees there. So they don't actually line up together. They're going to be slightly off. And so here on this image, you could see that the Earth is slightly on its side there. And then in this case, we have the Earth we have that celestial pole on top there, and then the Earth with that slight twist. There are many constellations, 88, but there are 13 of them that are of interest to us. As the sun goes around in the night sky, or as it passes through its path, it appears that it's in one of these constellations. And it always goes through the same constellations because the sun travels on the ecliptic. And so it would appear, for example, in like June or May, when you are born, it appears that the sun is traveling through the path of Taurus, right? The great bull in the sky there. And so it's the parent location of the sun in those constellations where they come from. But there's actually 13 of them. There used to be 12, right? Because 12 months, but they needed a modification there. Epicnus here, it was the 13th one. It actually passes right through the foot. And so we had to insert that back in. So if you do follow astrology, which again is not science-based, but if you follow astrology, you have to incorporate the other missing zodiac there. So there is in fact 13. A bit more of definitions here. Altitude, position above the horizon, and then your azimuth, we go clockwise around. So if we were to break up all around us, right, a circle makes 360 degrees. If we go all the way around, so making up 360 degrees, well, if you break those up, you could break it up into minutes. So each degree will have minutes, and then each of those minutes you could break up into seconds, so 60 seconds. And so if we want to have an exact pinpoint of a star, then it's easier for us to say that it is 34 degrees, altitude, so above the horizon, and then 42 degrees inward. So we're able to look up and then actually go kind of rotating. Same way as in an algebra class where you were plotting an XY point, but here we're doing this on the celestial sphere. One other definition here is the meridian, and the meridian is just an imaginary line that breaking up the sky into two regions, so it goes from north to south. And so the meridian here, if you're up on your Latin, AM and PM, so pre-meridian, post-meridian. And so that's why we have AM and PM. It's a location of the sun where it's at relative to that imaginary line. And so why do stars rise and set? Well, it's because the Earth is rotating. And so the Earth rotates from west to east, so it appears that the stars are going from east to west. So as we rotate, we could see the stars. It appears that they're rising and they're setting. Some stars are considered circumpolar, and what that means is that they never appear to rise or set. So what happens is a star will rise, come up in the sky, and then it will set. And so from our vantage point, it goes below the horizon and it appears to set. Well, if you're high enough on your latitude here, this star here will rise and it won't actually drop below the horizon here, and it'll come back up because of our slight angle there. And so what happens is this star doesn't appear to end up to set or to rise. It just stays up in the sky. And again, further up, you could see somewhere it would be more noticeable as we get closer and closer to the poles there. So that's what we consider a circumpolar. And here are just some images. So stars near the celestial poles, and this is a time lapse. So if you're familiar with photography, just opening up the lens, and we're capturing a kind of a time lapse here. Over perhaps several hours or so, and that gives that streak. Wandering stars. So as we looked at the night sky, there we noticed that some of the objects there moved a little bit faster than others. So planets, since they're closer, tend to move through the night sky a bit faster. And so initially they were giving the word wandering stars, so wanderer, and that's a Greek word for planet. So Mercury, Venus, Mars, Jupiter, and Saturn were the stars that were visible with the naked eye, or easily visible with the naked eye. Those five, in addition to the sun and the moon, make up 7, and that's where we get the 7 days of the week. So Sunday, the sun, that's fairly simple, but something like Viernes, Friday, is named for Venus. So why do we study astronomy? And today we have the kind of the luxury of studying it for curiosity. But inherently, it was really for keeping track of time and seasons. It was, we needed to keep track of it for agricultural reasons, a lot of times for ceremonial as well, and also for aiding in navigation. Older views of astronomy, since we've studied it since the very beginning here, really the oldest science. Some early models of the universe here is that they believed that the Earth was a great island carried on the back of a turtle. Later adapted is they thought that it was perhaps a 3-tier world where you had the underworld underneath the Earth, and then we had the heavens floating above there. So some very preliminary ideas or models of the universe here. And of course, being with science no absolute truth, we always allow ourselves for the modification of those ideas. And so this geographical a region here really explains why we study that scientific method here. And so early Greek Roman cosmology, we owe a lot of what we study today to those civilizations there. And so it really has to do a lot with location. So during the conquest of Alexander the Great, we see here in this map that we have 3 continents. So Africa, and then we have Europe, and then Asia as well coming together. So there was a lot of trade within this region. And so if you controlled that area, you not only controlled the wealth that came through there, but also you had a lot of influence in your ideas. So during the conquest of Alexander the Great, this region was captured by them, by his empire, and its influence, ideas were pushed throughout the world. So they tried to follow the scientific method, where we wouldn't use explanations of a divine intervention. We wanted things, to be observation and by experiment. And so it's because of the Greeks that we follow that scientific method. Now, had another empire had control of that region, it's possible we could have had a different method to what we consider modern science. So not to say this is the best method, but this is the current method, and this is where it developed from. Models are very important here, and you can see the Greeks making models very, very early on here. So they were known to make kind of the first models of nature here. And so we'll look at a couple here. Again, these were used to describe phenomena, trying to stay away from that kind of a divine intervention. Aristotle, so the Greeks knew a lot of interesting things here. This is in about 384 to 322 BC. They already knew the Earth was round, right? We talk about Christopher Columbus, 1600s or so, talking about that the Earth was still flat. This was known very early on. The sun was further than the moon from Earth, right? We knew all of these ideas here, and we could see because the shadow that it casted during an eclipse. The only object that would make a perfect circular shadow from all angles is a sphere. So this was known very, very early on. We also knew that, but one of the downfalls here was that they thought the heavens must be perfect. So they thought everything should be perfect circles, perfect spheres, and then they put us at the center of the universe. So things we know now that are incorrect, but they held true to these values, and this was one of the downfalls of the Greeks, where they weren't able to push some of their ideas forward. But even here early on in about 310 to 230 BC, with Aristarchus here, he had suggested that the Earth was moving around the sun, so that there was a heliocentric model here. And so one of the reasons that they did not believe that the Earth was moving around the sun is this idea of stellar parallax. And so if you're looking at a star from one vantage point, here it appears to be on the left side. But if we travel half a year later to the other side and we look at the same star, now it's going to appear to be on another side. So the shift of those stars would appear to move back and forth with stellar parallax. And since we're not able to detect that, then they determined that the Earth could not be going around the sun, and so they hung on to a geocentric model of the Earth at the center rather than the correct heliocentric with the sun at the center. And the reason why they couldn't detect it is because the stars are so far away, they could not comprehend the vast distances of stars. Here is Aristophanes here. This is 276 to 194 BC. Again, already knew the Earth was round and actually came up with an estimate for the size of circumference of it. So 40,100 kilometers versus 4,200 kilometers. So very, very accurate there. Was slightly off and used this idea of kind of shadows to make a sense of that, knowing the distance of two objects in different cities and the distance between them. And then he was able to calculate the angle between them and got a very accurate estimation for the circumference. So very early on, we had these ideas of knowing the Earth was round and with estimations, and then also knowing that the sun was at the center. Hipparchus here in 150 BC knew about precession, and that's that the Earth also moves around like a top. So apart from it rotating, it moves like a top, kind of wobbles around. And so where our north is pointing at changes. Currently, Polaris is the North Star, but later on, Vega will be the North Star. This cycle takes about 26,000 years. So not only was it aware of that, he was able to monitor that for some time and do these calculations there. Ptolemy gets credit for his model, which reigned for about 1,500 years. So it was an incorrect geocentric, but it did a very good job at predicting placement of planets. One of the issues was retrograde motion, the apparent motion that a planet is moving backwards through the night sky. It doesn't really move backwards, but it appears to go backwards. So in our orbits, as Earth passes it up, we're going here and we're passing it up, then Mars here is ahead of us. Then we catch up, and then it starts going behind us. So it appears that it starts moving behind us in backwards motion. And so that model had difficulties explaining that. And this happens over a couple of weeks. So Ptolemy modified the model and said that not only are we going around, we're also going around the Earth in little circles. And so when the circle is coming backwards, that explains that apparent retrograde motion there, that apparent motion of going backwards. And it was a a fairly good model in terms of predicting and accuracy there. So it held on for about 1,500 years where they could predict the location of certain planets. Now, look at the time frame here. It's not till about 1473, 1500s or so. So that whole time frame, almost about 1,500 years later, that we start coming up with some new ideas in astronomy. And so Copernicus, again, held on to that model, although incorrect. It explained things fairly accurately. We call that kind of the Dark Ages because just there wasn't really advancement in science. So Copernicus had started this revolution here. And he talked about a heliocentric model. Now, again, he was not the first to come up with this idea. We know that some of the Greeks had this very early on, but he kind of revitalized this idea and started pushing it forward again, and made a publication, right, in 1543 here about this a heliocentric. And he was also able to lay out the models in terms of AUs, distances from the sun. Now, his model was not that much more accurate than Ptolemy's in predicting locations of the planets in the night sky. So remember Occam's razor, all things being equal, we're going to go with this simplified model. We're not going to pick a new model that changes our understanding of the location of the Earth and the sun. So it was a little bit difficult to push this idea forward. Tycho Brahe helped in this. Tycho Brahe was a royal astronomer here. And so very smart, very arrogant. So the story goes there. One time during a confrontation about mathematics or so, he got into a duel with someone and lost his nose in a sword fight there. He had to use a prosthetic nose for some time in his life there. But he was very particular, and he was able to get funding for them to do it a royal observatory. It was more of a palace. So he had lots of instruments, and he was able to track the motions of the planets, and he was very accurate to about 1 arc minute. He later hired Kepler, Johannes Kepler, as his apprentice to help him out to kind of keep track of everything. And it's really Johannes Kepler that gets credit for his work there. In his deathbed, Tycho Brahe, had told Kepler, don't let my work go in vain. Take what I've done and, do something with it. So Kepler went over all of his calculations, and he noticed that there was an 8 arc minute of discrepancy. So again, think of all around us, 360 degrees in a circle. If you break one of those up, you could break it up into 60 minutes. So 8 arc minutes, very, very small measurement there, that he was slightly off. And so this was two things. Either Tycho Brahe was incorrect in his measurements, or the planets did not orbit around in a circle. They actually orbited around in an ellipse. And so Kepler thought about it, and he said, Tycho Brahe is so particular, there's no way that he could be wrong on that. And so he went over the calculations there, and later on he came up with his laws of planetary motion. But it wasn't really until Galileo here, so 1564 to 1642, that started tying all these ideas here and really getting some kind of arguments going for them. So Galileo's really solidified all of those things and started pushing what we consider our modern science forward. So Galileo, the story goes that he threw objects off the Leaning Tower of Pisa to show the effects of gravity there. Not really true. That's more of a fable there. You would have needed something a lot taller than there. And then Galileo also sometimes is getting credit for inventing the telescope. He did not invent the telescope. Sailors had it long before, but he was one of the first to use it to look at objects in the night sky, including the sun. And do not ever look at the sun with your eye. Galileo went blind towards the end of his life for doing so. Galileo observed a couple of things with just his telescope. That's probably, you could find a pair of binoculars today that are more powerful than the telescope he had. But he observed 4 moons orbiting around Jupiter. And so we call them the Galilean moons. He also looked at the sun and looked at sunspots. So these cooler regions that cool down, and we could see that the sun was not a perfect sphere. Also the moon, noticed mountains and valleys. But one of the most important things was the phases of Venus. He was able to look at the phases of Venus, and this would only be possible if we were in a heliocentric. So the Earth and Venus orbiting around, then we would be able to see those phases. If we were not in this alignment, we would not be able to detect those. So how did Galileo solidify the Copernicus revolution here? Is that he overcame these 3 things. Earth could not be moving because objects in the air would be left behind. So this is one of the things that they thought, the Greeks, that if we're moving around, if something jumps up, it's going to fly off. So think about being in your car. You have your iPhone with you. When you're driving, if you were to toss your iPhone up in the air, it doesn't fall backwards to the person in the back seat. Everything is moving together so that velocity pushes forward. Non-circular orbits are not perfect. So remember, they thought everything was perfect. Perfect circles, the heavens have to be perfect. And he started to observe some items that were not perfect circles. And then if Earth were really orbiting the sun, we would detect stellar parallax. And that was one of the main issues for us orbiting around. So Galileo showed some of these experiments here. So Aristotle thought that objects naturally come to rest, and Galileo showed otherwise. And later on, Newton took some of that to make his laws. So again, as things are moving together, tossing an object up in a car, you all move forward together. Sunspots that he saw, mountains and valleys on the moons, he noticed that those objects were not perfect spheres, perfect circles. So the heavens are imperfect. The moon's orbiting around Jupiter. You could have an object orbiting around something else other than the Earth. And then he observed the phases of Venus, which again indicated that the sun had to be at the center, not the Earth. So, also, with Tycho brought his measurements, the stellar distances, the parallax was, something that was shown there. But Galileo actually showed that the stars must be further than Tycho thought. So they thought they were kind of closer, but recalculating that with these larger distances, he concluded you wouldn't be able to detect stellar parallax if, in fact, these stars are further away. So he was able to kind of answer all the issues that the Greeks had of why we cannot put a heliocentric model there. And Galileo had discovered this. I mean, he's one of the few scientists that you call by one phrase, Galileo Galilei, right? Kind of the Madonna of our time. These famous people, you just put one kind of phrase on them, Prince, right? So he was kind of a celebrity, just called Galileo. And he published this, and rather than being, honored, the church actually put him under house arrest. They burned all of his readings. They prohibited, they banned everything. And so it wasn't until he was really on his deathbed that he passed that stuff on, now that they couldn't do anything to him. They're like, here are my publications, push these out, get them out to everyone. And, now we know he was correct, but it wasn't even until 1992 that the church formally, issued an apology for that, for banning all of his things. And this is common, when you have these new ideas of something like the Earth not being at the center, that it's the sun. It challenges these larger ideologies of a person. And the church had a lot of issues with that because it didn't want to give up some of the powers it had. So currently in science, this is happening as well. Very difficult to push new ideas forward. We try to be open, but it's a common issue that comes up.